Hello, everyone, and welcome to my presentation about the development of a new generation of neurovascular device for the treatment of cerebral aneurysms with complex anatomy. My name is Mehdi Jahandar, and I am a PDF at the University of British Columbia in Canada. And this is a joint project between UBC and Evasc Neurovascular Enterprise. Cerebral aneurysms are abnormal dilation of the cerebral arterial wall, and they are responsible for more than 500,000 deaths each year worldwide. Flow diverters are the recent technology that have been developed for the percutaneous treatment of cerebral aneurysms. For example, one example is the pipeline stent, as you can see on the left image. It is a Medtronic's device. It is working by redirecting the major portion of the flow into the daughter vessel in which it is implanted, and is imposing a high pressure drop and high flow resistance to the flow entering the aneurysm, at the same time to the other daughter vessel, which is highly unfavorable. Evasc Neurovascular Enterprise has developed a breakthrough device. It's called eCLIPs. It is percutaneously positioned at the neck of the aneurysm, as you can see, to alter the flow. It has some benefits over other flow diverters. For example, it does not occlude the daughter vessels, as you can see, and it bridges the neck and prevents aneurysm inflow. However, there are some subset of bifurcation aneurysm with fusiform pathology that they have a very complex anatomy, and they are very, very difficult for treatment. As you can see, when we implant the eCLIPs at the neck, there's a large gap between the device structure and aneurysm wall that causes inadequate neck bridging. What we have proposed to tackle this challenge is to extend the ribs at the center to close the gap entering the aneurysm, as you can see section B and section C over here. We started by developing a model for fusiform bifurcation aneurysm, implanted the eCLIPs at the neck, and extended the ribs at the center to cover the gap, as you can see over here. We utilize computational fluid dynamics to assess the hemodynamics of the new design over eCLIPs, and results show considerable aneurysm inflow reduction. For example, the ratio of the aneurysm inflow to main artery flow is 99% for the no device case, while it is 92% for eCLIPs. It is not sufficient, but it has decreased to 66% for the new design, as you can see over here and over there. Result also indicates significant aneurysm wall shear stress reduction. For example, as you can see on this image, this is a new design or eCLIPs modified design, eCLIPs and the no device case. Results also indicate the aneurysm inflow reduction is 7% for eCLIPs, while it has increased to 33% for the new design. And aneurysm wall shear stress reduction is 24% for eCLIPs, while it has increased to 53% for the modified design eCLIPs or new design. As a conclusion, the result of our study clearly indicate the effectiveness of the modified design eCLIPs in promoting thrombosis inside the aneurysm dome for bifurcation cerebral aneurysm with fusiform pathology. And the new design can represent the only available device for the percutaneous treatment of such complex aneurysms. For the future work, we intend to use patient-specific aneurysm geometries with more sophisticated numerical model, such as non-Newtonian flow model and compliant aneurysm and arterial wall, which requires fluid solid interaction modeling. And we are in process of developing a finite element model to simulate the device life cycle, which is crimping into the catheter and expansion at the aneurysm neck. I would like to acknowledge the contribution of our research team at UBC and Evasc, as well as the sponsors of this project. These are some selected scientific contributions, and thank you for your attention.